get to have calculus before that. Your day just got better? Nice. Also, perhaps if it makes your day better, we have this thing called squeeze theorem that we're going to discuss shortly. I heavily considered putting a picture from Neon Genesis Evangelion here, where Unit 1 is squeezing Kaworu, but I decided against it. I don't know if anyone here has seen Neon Genesis Evangelion, but it's one of my favorites. Anyway, today we are, yep, I'm about to start the recording now. Today we are going to finish up section 2.3. And once we finish up section 2.5, we are going to acrobatically leap over section 2.4 without looking back at it at all. And continue on our merry way. So we are going to jump right over 2.4 and hop into 2.5 instead. Sound good? I highly encourage you, however, on your own time to read through section 2.4. Section 2.4 is on the precise definition of a limit. The reason why I'm not covering section 2.4 and why some other instructors also don't cover section 2.4 is, first of all, it's my class. And second of all, how many of you are math majors? How many of you are going to major in mathematics? Statistics is a different major. I don't say that disparagingly. I say that because of the necessity of knowing this information. So, if you are going to be a mathematics major, and perhaps if you're a statistics major and you're also curious, I would definitely read through section 2.4. Section 2.4 will help you improve your mathematical maturity. It is on the precise definition of a limit. It is the delta epsilon definition of a limit. It is very pure mathy. It's very abstract and pure mathy. But my thing is, even if you're going to be a math major, Sylvester, if you become a math major, you'll definitely have to take real analysis. I'm not sure I don't think that stats majors have to take real analysis, which is why I'm mentioning this. In real analysis, you'll just learn it again. Anyway, but I do recommend looking at 2.4. Well, you have to learn real analysis to learn complex analysis. I believe that a lot of complex is predicated on real analysis, although many people much prefer complex and the beauty of complex analysis. Anyway, so I encourage you to read section 2.4, is what I'm saying. It is interesting, and maybe after we do 2.5, we'll skip back and look at it if we have time. Until then, we're continuing on. We're about in the middle of 2.3 here. We're discussing when are we going to use one-sided limits? Well, some limits are just best calculated by finding the left and right-hand limits. We have a theorem, and we've kind of seen this before. The limit of f of x as x approaches a is equal to L, if and only if. The limit of f of x as x approaches a from the left is equal to L, which is equal to the limit as f of x, or of f of x as x approaches a from the right. Does this make sense? L is an arbitrary number. It's just some number that represents the limit value. So it's just saying that this limit is equal to whatever number the limit is, if and only if the left and right hand limits are both equal to that number. Awesome. And we've discussed this before, but I think it was in terms, I think it was slightly different. No, this is still 2.3. We're about in the middle of 2.3. So let's show that the limit is the limit of absolute value of x as x approaches 0 is equal to 0. So how should we do this? We can't necessarily use our direct substitution property right away, right? Because our direct substitution property is predicated on f being a polynomial or a rational function. And the absolute value function is not a rational function or a polynomial. However, I can define absolute value of x in a different way, right? Do we recall that absolute value of x is kind of the quintessential or prototypical piecewise function? This is a way in which I can define absolute value of x. Do we agree? The reason we're doing this is because we're discussing left and right hand limits. I know that I can find left and right hand limits of these two things super easily, right? Since I have this alternative definition available to me, let's use it. So this gives us a function to use for a right hand limit and a function to use for a left hand limit, doesn't it? Because absolute value of x is equal to x for x greater than 0, right? This means that the limit as x approaches 0 from the right is equal to the limit as x approaches 0, of absolute value of x is equal to the limit as x approaches 0 from the right of x. Do we agree with that? And now I can use my direct substitution property because x is a polynomial. So this is just 0. I can plug 0 in here. And absolute value of x is equal to negative x for x is less than 0. This means that the limit of absolute value of x as x approaches 0 from the left is equal to the limit of negative x as x approaches 0 from the left. And using my direct substitution property, this is 0. So notice that my left and right hand limits are in agreement, right? I can say that the limit as x approaches 0 from the left of absolute value of x is equal to the limit of absolute value of x as x approaches 0 from the right. And because these two things are equal, they have to equal the limit. Maybe I should have said is equal to 0, right? Somewhere in here. And this has to be the limit of absolute value of x as x approaches 0. Do we agree? Yes. Also, please excuse my inconsistent readings of these limits out loud. Some math instructors and professors are real sticklers about the way in which you read this. I don't know. I feel like I've never heard a single consistent way. I think there is a right way, and I think the right way is the limit of absolute value of x as x approaches 0 from the left. But my brain wants to read everything on the left first. So, you know, as long as it's written correctly, that's all I care about. If you say it out loud incorrectly, my brain's probably going to process it fine. As long as you write it correctly, make sure that when you write your limits, that you write them correctly with the LIM and below it, variable approaches number. Is that okay? Are we okay with my inconsistent readings of these? Yeah. Again, some people care a whole lot about it. This isn't something. Whether you read this out loud properly or not does not mean a lot to me, right? What means a lot to me is that you write the notation correctly, and that you're able to understand the mathematics. Let's prove that this limit does not exist. Huh. What should our first step be? Do we have a problem? Have we seen a problem similar to this one in recent memory? No. What about the problem we just worked out? Let's rewrite this absolute value function again. Let's rewrite this absolute value function. Remember, the absolute value of x is equal to x for x greater than 0, right? And absolute value of x is negative x for x less than 0. And this works out nicely for us because this is the limit as x approaches 0, right? So an identity... What are we waiting on? Because if x is less than 0, then absolute value of -2, for instance, is -2, which is +2. Does that make sense? This is just the way in which we defined this a second ago, right? It does. Absolute value of -2 is +2. Because -2 is +2. For x less than 0. For x less than 0. It is. Does that make sense? If x is less than 0, yeah, this is just a piecewise defined function. Yeah, exactly. This allows me to have an easier time. No problem. It happens. Sometimes I get confused while I'm working a problem. So, you know. And I'm the teacher. Maybe I shouldn't have admitted that, huh? Y'all are going to show this recording to my boss. So this is what I have. The limit so far. The limit as x approaches 0 from the right of absolute value of x divided by x is equal to, well, I suppose I should say, the limit of x divided by x as x approaches 0 from the right. Because for x greater than 0, absolute value of x is the same thing as x. And we are dealing with the x values greater than 0 here. Well, x divided by x simplifies nicely, doesn't it? X divided by itself is 1. And the limit of the constant is that constant. Similarly, the limit of this function as x approaches 0 from the left is equal to absolute value of x is negative x for all values of x less than 0. Here we get a negative 1 as our result. So this limit's equal to negative 1. So, because the limit as x approaches 0 from the left of this function does not equal the limit as x approaches 0 from the right of this same function, this means that the limit of this function as x approaches 0 does not exist. Does that make sense? So because the left-hand limit is not equal to the right-hand limit, the limit of this function as x approaches 0 does not exist. Awesome. And if you're telling me that a limit doesn't exist, you should probably provide some kind of justification like this, right? You should tell me why the limit doesn't exist. Otherwise, I might think that you're just trying to make something up. Right? Also, I'll be grading your labs during these work days since y'all have spring break. I don't, but I'll be using some of these work days to grade your labs and stuff. So I'll probably get those in tomorrow or Wednesday. And I'll go ahead and type in your web assignment while I'm at it. Tomorrow, Wednesday, and Thursday is your spring break. So let's look at this. If we have this piecewise defined function, f of x equals the square root of x minus 4 if x is greater than 4, and f of x equals 8 minus 2x if x is less than 4. Determine whether the limit as x approaches 4 exists. And in this case, we're not only going to be able to determine whether, really, it shouldn't just ask if it exists. It should also ask, and if it does, find it. There we go. Because with the tools that we have currently, if we're able to determine if a limit exists, then we're also able to, I don't have a certain Desmos thing, no. I don't have anything special set up in Desmos for this class. All you need is WebAssign. What kind of things do people do with Desmos codes? Maybe I should look into that. If you've had that before, send me an email about that, because I'll look into doing that in the future. Oh God, don't even get me started on NFTs. Let's just keep going. So with the tools that we have currently in our toolbox, if we're able to determine if a limit exists, then we're also able to find the limit, right? So this problem should say find the limit as well. So we're going to find a right-hand limit and a left-hand limit. And if those two limits are equal to each other, then we have the limit. Do we agree? Okay. No. No, we have to find a left-hand limit and a right-hand limit here. We have to find the limit of f of x. I'm going to write the limit of f of x as x approaches 4 from the right. Hey, spoilers. This is the limit so as x approaches 4 from the right, we're looking at all x values that are greater than 4. So we're looking at the first part of this piecewise defined function. So we're looking at the limit of the square root of x minus 4 as x approaches 4 from the right. This actually is a rational function, so I can use my direct substitution property. This is 0. Now the limit of f of x as x approaches 4 from the left, this is the limit of 8 minus 2x as x approaches 4 from the left. And here I can use my direct substitution property again because this is a polynomial. This is 8 minus 2 times 4 is 8, which is 0. So my left hand and my right hand limits exist. And my left hand and my right hand limits are equal to each other. So I have that the limit of f of x, I'll answer that question in just a second, as x approaches 4, exists and it's equal to 0. If these equations are reversed, would the answer be D and E? Let's see. If these were reversed, yeah, the entire second function would not be defined, right? So you wouldn't ever run across anything like that in a problem where the second function just has no domain. I wouldn't be cruel enough to give you something like that. Does this make sense? Excellent. Let's look at a theorem. The direct substitution property. The direct substitution property just says if my function is a polynomial or a rational function, if the function I'm trying to find the limit of is a polynomial function or a rational function, I can just take this number and just plug it in. And that's the limit. So I just plug this number in because this is a rational function. This is a rational function because this is just a polynomial that's being raised to a power. Should we check to see if it's in the domain first? In this kind of problem, that realistically shouldn't be a concern. Although, so you're asking, yeah, so if you plug in the number and you get something that is not in the domain of the function, obviously that limit doesn't exist, right? So in that case, you would say that this limit doesn't exist if you had to plug in something where if you had to plug in a number that would cause the argument to be outside of the domain of the function. Then the limit would not exist. Although sometimes functions can be very tricky and appear prima facie to not have a limit, even though they really do. So we have to be very careful. Will we see an example of this? We'll see. My answer is I'm not sure. Perhaps later on. Next up, we have the squeeze theorem. This is also known as the sandwich theorem, the pinching theorem. This thing has a lot of different names. If you Google squeeze theorem, it has like 20 names. The sandwich rule, the theorem of Carabinieri, the between theorem. Anyway. So before we get to the squeeze theorem, let's look at this other theorem. If f of x is less than or equal to g of x when x is near a, except possibly at a, and the limits of f and g both exist as x approaches a, then the limit of f of x as x approaches a is less than or equal to the limit of g of x as x approaches a. Does this make sense? Does this first limit, or this first theorem 2 here, make sense? This is saying that the function values of f are all less than or equal to the function values of g whenever x is near a. Right? Then, as long as the limits of these functions both exist, I'm talking about this first one right now. As long as these limits both exist, then the limit of f of x as x approaches a has to be less than or equal to the limit of g of x as x approaches a. Oh, number 1? Was there number 1? Number one was the one-sided limits thing that was all the way up here. Number 1 was just this one-sided limits thing up there. Yeah. Now, the squeeze theorem tells me if f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a, except possibly at a, and the limit as x the limit of f of x as x approaches a is equal to the limit of h of x as x approaches a, which is equal to some L, then the limit of g of x as x approaches a is also equal to that same number L. Does that make sense? If I have these two functions that are respectively effectively above or below, right? Above and below or equal to this middle function, and those functions have the same limit as x approaches a, then the limit of g of x as x approaches a has to be the same as those two functions, the limits of those two functions that are sandwiching it, essentially. Yes, f and h are squeezing g. Yes, exactly. F and h are squeezing g, or f and h are sandwiching g. Yes, that's correct. Does that make sense? Let me show you an example. Well, let me show you a picture. Picture's worth 1,000 words. So maybe that saying was invented in a time when it was much more difficult to take a picture. So here we have functions f, g, and h. Notice how g is being squeezed or sandwiched by f and h. Sometimes I know the limits of f and h as x approaches a. So you see that if the limit of f of x as x approaches a is that number L, and the limit of h of x as x approaches a is equal to that L, and g is either between these two functions or equal to them, that g has to have that same limit as x approaches a. Do we see that? Necessarily. Okay. This is once we see a picture, a lot of the time this becomes one of those things that seems like a no-brainer almost, right? But this is a very useful theorem. Essentially, these two functions are forcing g to take on the same limit, right? Now, this is going to be useful in an example like this. Because you might be wondering, when am I ever going to know the limits of h and f, but not the limit of g? It's probably going through our mind, right? Yeah, this seems cool. It seems maybe obvious once we look at it, but when am I ever going to know this information? Did we think that at all? Well, we're about to look at an example. Low key, yes. Okay. Show that the limit of x squared times sine of 1 over x as x approaches 0 is equal to 0. We can find this limit using the squeeze theorem. In order to apply the squeeze theorem here, we have to find a function f that is smaller than this function and a function h that is larger than this function, such that f and h both approach 0 as x approaches 0. Does that make sense? We want to find function, no. Here, let's type it out. Let me make the font larger. Let's type it out. Closed captions. We need to find a function f smaller than g and a function h larger than g, such that f of x and h of x both approach 0 as x approaches 0. In order to prove this, right? In order to show this, we're told that it is true, basically, right? We just need to show that it's true. So to do this, we are going to use our knowledge of the sine function. Okay. I can squeeze this sine function between two numbers. What do all of the outputs of the sine function have to be between? The sine of anything is between -1 and 1, right? The range of the sine function is -1 to 1. Do we agree? So in other words, do we agree that -1 is less than or equal to sine of 1 over x, which is less than or equal to 1? Now, any inequality is true if I multiply everything in the inequality by a positive number. The inequality stays true. So I want x squared times 1 over x, right? So I'm going to multiply everything by x squared to get this original function f that I started with. We following so far? And I can find the limit as x approaches 0 of these two functions, right? What's the limit as x approaches 0 of x squared? Well, I get to use the direct substitution property here. Same thing with negative x squared, right? I get to use direct substitution. So the limit as x approaches 0 of this function. Has to be 0 because it's being sandwiched between these things by the squeeze theorem. And if we were to graph these, we would see that this function is being sandwiched between these two functions. Maybe let's throw this in Desmos. Just to verify that this is in fact being squeezed between these two functions, right? Maybe we're skeptical. But this looks pretty convincing, don't you think? It looks pretty convincing to me that the green function here is in fact being squeezed between the blue and the red functions. Cool. How did we multiply by x squared? We're allowed to multiply everything in an inequality by a positive number and keep the inequality. X squared will always output a positive number. So we're allowed to multiply everything in the inequality by x squared. Does that make sense? And the reason, the reason we did it is because we noticed that I have sine of 1 over x in the middle of the original inequality, but my function f is x squared times sine of 1 over x, right? So I really want to get x squared times sine of 1 over x in the middle there. And the way I can do that is by multiplying through everything by x squared. And that's 2.3. We did it. We conquered 2.3. So it's time to discuss continuity. Let me create a new section group here. This will be called 2.5. I like that I have so far kept everything that we've done since I have actually used them to go back and reference. This will be on continuity. There we go. Continuity is a bit of a weird word, right? There we go. So we discussed how sometimes we can find the limit of a function as x approaches a just by plugging a into the function. Sometimes we can use the direct substitution property, right? Functions that have the direct substitution property where the limit of a function is equal to its function value at that number, are said to be continuous at A. We're actually going to see that our mathematical definition of continuity pretty closely corresponds to the meaning of continuity that we use every day, right? What do we think of continuity? What do we think of when we think of continuity? Typically. And what context do you think of that word in terms of? Time. Use it at work. In what way do you use it at work? Describe a continuous process. Is no one gonna? Okay, I'll say it. I think of like TV shows, right? I think of like TV shows or like movies, right? Like, have you ever noticed that sometimes, like in a scene in a movie, like, you know, the camera cuts away and it cuts back and something's changed in the background? Have you ever noticed like things like that? Or like an actor's hair looks different whenever they cut back? Things like that. Those kinds of things are called continuity errors, right? We expect for things to be exactly the same whenever they cut away the camera, right? And come back to it. So this is the kind of thing. yeah. So that's the kind of thing that I think about whenever I think about continuity. Honestly, very similar idea in terms of mathematics. Here's our mathematical definition. A function f is continuous at a number a if the limit of f of x as x approaches a is equal to f of a. So if the limit of f of x as x approaches a is equal to its function value at a, then we say that this function is continuous at a. Does this make sense? Of course. Okay. Here is a picture. This is how we like for functions to behave, right? Whenever functions behave like this, it's nice, right? There's usually nothing, you know, usually the really difficult stuff starts whenever we have to start dealing with things like asymptotes, right? So it's really nice whenever we have a function that's continuous on its entire domain. Now, there are a few implications. There are a few things that are implicitly required for something to be continuous at A. These are my 3 implied requirements for a function to be continuous at A. Surprised no one's asked me what kind of keyboard switches I have yet. They're Cherry MX Brown switches, in case you were curious. I have a Ducky Year of the Dog edition. First of all, f of a has to be defined. This means that a has to be in the domain of f. Yeah, they're mechanical Cherry MX Brown switches. I have a Ducky Year of the Dog edition. It's top notch. It was like $220. The limit of f of x as x approaches a has to exist. And the limit of f of x as x approaches a has to be equal to f of a. That's the only part that was actually in our definition, right? These other two are implied. Does this make sense? Do these implications make sense? Yes, yes. Yes. The typing is very satisfying. Okay. So this definition is saying that f is continuous at a if f of x approaches f of a as x approaches a. So a continuous function has the property that a small change in x causes only a small change in f of x. Right? Does that make sense? A small change in my x value in a continuous function shouldn't cause an extremely large change in my y value, right? Because there shouldn't be any huge jump. Does that make sense? There should be like a smooth curve whenever we zoom in on the function. Nothing too crazy. Okay. In fact, the change in f of x can be kept as small as we like, as long as we keep the change in x sufficiently small. That's actually part of what 2.4 is about. Now, if f is defined near a, let me type this out for us. If f is defined near a, or we say f is defined on an open interval containing a, except possibly at a. We say that f is discontinuous at a. Or f has a discontinuity at a. Maybe I should put a in quotations here. How is this different from this? Is that what you're asking? So if f is defined near a, but not at a, then we have a discontinuity at a, is basically the idea. That is, I left out a part. If f is not continuous at a. So it's just saying if f is not continuous at a, but it is defined near a, then we say it's discontinuous at a. Not continuous, discontinuous. Sense? Physical and natural phenomena are typically continuous phenomena, right? Discontinuities do occur in some natural phenomena and in some physical phenomena that we can observe. We discussed the Heaviside function previously, which represents a switch being flipped at time t equals 0, right? And current going from 0 to 1. So in situations like electric currents, discontinuities do occur in the physical world around us. Geometrically, we think of a function that is continuous at every number in an interval as a function whose graph has no break in it, right? This is probably the definition that we're most familiar with if we've heard this before. We think of it as a graph that can be drawn without removing your pen from paper, right? So any graph of a function that you can draw without removing your pen from paper is going to be continuous. But if you have to remove your pen from the paper, you create a discontinuity. Does that make sense? Gotcha. Okay. Let's look at an example here. I'll give us a figure. We have to figure out the example. Oh, pun 100% intended. All right. Figure 2 here shows the graph of a function f. At which numbers is f discontinuous? Why? One, three, five. Okay. 1 through 5. Do we say 1 through 5? Okay. So whenever, well, this thing a is equal to 1. So at x equals 1, what causes the discontinuity here? Okay. The cause here is there's a break in the graph. There's a hole, right? Yep. What about x equals 3? What's the cause? So we kind of have a bit of a multifaceted cause, yeah. Limit does not exist. And f of 3 is defined, right? F of 3 is defined, although the limit does not exist, right? F of 3 is equal to whatever value this dot has, right? Although maybe we can say though f of 3 is defined, right? We could say f of 3 is defined. That's one of our check marks. That's one of the things that we need for this to be continuous, right? F of 3 is defined. The other thing is that the limit exists and is equal to this function value. And x equals 5. What's the cause of the discontinuity there? It's slightly different cause. Yeah, the limit as x approaches 5 of f of x exists, but is not equal to the function value. So this limit exists, right? Because if I calculated my left-hand limit and my right-hand limit, they would both be whatever this y value is at this dot, right? But that function, that limit value is not equal to my function value, and my limit value has to be equal to my to this function value in order for this to exist. In order for this to be continuous, rather. The function value is this dot up here. That's f of 5. This closed dot here is defining the function value. Does that make sense? Well, this is just asking us which numbers it's discontinuous. So the limit exists, but the limit is not equal to f of 5. And this is what's causing this discontinuity. Yes.
So what would we call the function of that dot? Is that part of f of x, or is that something else.
Uh-huh. It's part of f of x. This is all made in a piecewise way. So this part here would be defined on its own in the piecewise function. There would be a part where it would say like, in the piecewise function, it would have whatever the function is, and down at the bottom, it would have something like 3 whenever x is equal to 5. And that would define this dot. Does that make sense? Awesome. Let's look at some examples. You shouldn't apologize. Other people have questions as well. And, I'm certain that you are asking questions that other people have. She is for sure. Yeah, see, immediately. Right. Typically, if you ask a question, other people have that question. So don't be afraid to ask questions, right? So let's look at where are each of these functions discontinuous. Oh, and this function here, I skipped over it, but this is the greatest integer function. Let me skip back to 2.3 real quick so I can just briefly discuss this. Blah, 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 blah. So the greatest integer function just defines, I'm not sure exactly how to write it out. I suppose, well, I feel like you write it out like this. If you write it, I feel like you use this. This is a seal, or you could call this a ceiling function, I suppose. This is equal to the largest integer that is less than or equal to x. Oh, I guess this is a floor function. Never mind. The largest integer less than or equal to x. For instance, this greatest integer function of 4.8 would be 4. Or of pi would be 3. Or of 2 would be 2. Yeah, round down, but like just drop any decimal place, basically, right? Drop any decimal. Yeah. So drop any decimal. Yeah. That's the idea of this function here. So let's look at where each of these are discontinuous. And I have to be right back real quick. You don't feel like the sections in the lab reflected the notes in the textbook? 1.5.3 was irregular? Let me check that for you. Let's see. The quick prep stuff was awesome. Cool. Yeah. I'm glad I saw that stuff. Are you talking about that section in the textbook that I pointed out? Yeah. 1.5.3? Just in general? Okay. Expand the logarithmic expression. Yeah, I mean, these should line up. The first number at least should line up with the appropriate section. Each of the numbers should have lined up with the appropriate section. The third number, I borrowed and repurposed and modified a lab from a colleague. I just didn't change the the third number there probably just indicated originally. This is the first question from section 2.2, for instance, and this is the second question from section 2.2. I just modified a previous assignment, so I believe that's what those numbers meant. All right, let's get back to this here. So what did we come up with? This first one. Where is this first one discontinuous? Yes. Our class notes should align with the schedule. Our class note... our class nights should align with the schedule that's on our syllabus. Yeah. Roughly, with a slight flexibility, although for like the most part. So, first of all, here, notice that in A, what's the easy one? What's the easy discontinuity to notice here? Oh, come on. Yeah, X can't be 2, right? That's the easy one. Sorry, not to make fun of you, Sylvester. Sorry, I didn't mean it in a harsh way. I meant it in I expected better of you kind of way. Okay. Now, let's look at B. For B, where's B discontinuous? At 2. Okay. Why? Yes. So B is discontinuous at x equals 2. Because while it has this defined function value, right? I should say x equals 2 here, right? Because we're answering where they're discontinuous. So this is also discontinuous at x equals 2, because while f of 2 is equal to 1, this is defined, right? If I were to find the limit of this function, the limit as x approaches 2 of this function, we'd have to factor it. It factors to this. Notice the x minus 2's cancel. I can use direct substitution here. 2 plus 1 is 3. This is not equal to my function value. So I'm finding the limit as x approaches 2 of this function. All I did was I factored the top. The top factors to x minus 2 times x plus 1. Then I'm allowed to go ahead and carry out the division, which leaves me with just the limit of x plus 1 as x approaches 2. And then I can use my direct substitution property to plug 2 in here. The function from B, this top one. Yeah. So here I get a limit value of 3, right? But that's not equal to my function value. F of 2 is equal to 1. So this means that this is discontinuous at x equals 2. Does that make sense? Think so? Okay. What about for C here? Where is C discontinuous? At 0. And why? Why is it discontinuous at 0? At x equals 0. So the limit as x approaches 0 of this function is infinity, right? This function grows without bound as x approaches 0. Do we agree? This function 1 over x squared. Yeah, because the graph goes like this, right? This function grows without bound as x approaches 0. But it has a defined function value. So we could either say that the limit does not equal the function value here, or we could just say that the limit doesn't exist, because it technically doesn't. Right? We could just say that the limit as x approaches 0 of 1 over x squared does not exist, because these infinite limits aren't real limits, right? So does that make sense? Mm-hmm. And this last one. Where's the greatest integer function? Discontinuous. Define every number. It's not really every number. Every whole number, every integer. Yeah. Yeah. This greatest integer function is is discontinuous at every integer. Because if we were to graph that thing, right? The easiest way, at least, to describe this is that if we were to graph this, you'd end up with a graph like this, right? Anything between 1 and 2, you just assign it the value of 1. Anything between 2 and 3, you just assign it the value of 2. So the limit as x approaches 2, for instance, does not exist, right? Do we see that? Because there's a jump here, right? The limit as x approaches 2 doesn't exist. The limit as x approaches 1 does not exist. The limit as x approaches 0 does not exist. Does that make sense? So, we actually implicitly covered a few different types of discontinuities. So D here is D is discontinuous at every integer. Because because the limits do not exist at any of the integers. So we actually have a few different types of discontinuities in the problems that we just discussed. So let's give them names. These are actually graphs of all of the functions that we just discussed the discontinuities of. Let me go ahead and grab this thing real quick. So we can just put a function with each of these graphs. So A is A, B is B, C is C, and D is D. So for A and B, we have removable discontinuities. Whenever I'm able to factor a function and cancel something, this causes a whenever I'm able to factor a function and cancel out from my denominator something that was causing me to divide by 0 previously, like I did here, this causes a hole in the graph. This is called a removable discontinuity because we can remove it by just defining a function value there. We have what are called infinite discontinuities. These are also called non-removable discontinuities. Infinite discontinuities occur where we have vertical asymptotes. Just to put another something that we're familiar with to this. Infinite discontinuities or non-removable discontinuities occur where we have vertical asymptotes. And in D, we have a jump discontinuity because the function jumps from one value to another. The Heaviside function is also another example of a jump discontinuity. Does this make sense? Amazingly. So let's discuss left and right hand continuity. So there we go. In the same way that we can have left and right hand limits, we can have left and right hand continuity. A function is continuous from the right at a number a if the limit of f of x as x approaches a from the right is f of a, and this function is continuous from the left at a if sure there is. You have you have arms and a body. There's continuity, right? If the limit is x of f of x as x approaches a from the left is equal to f of a. So pulling up an example of where we might define, for instance, a left-hand or right-hand continuity, let me pull up what was called figure 2 before. Let me pull this up. Notice that we said previously that the limit, we said previously that this is discontinuous at x equals 3, right? We agree that this is discontinuous at x equals 3. However, we could say that this is continuous from the left. At x equals 3. because the limit as x approaches 3 from the left is equal to f of 3. Do we agree with this? Perfect. So this is the idea of having continuity from the left or from the right. Is sometimes we can't say that something is continuous at a certain number, but sometimes we can say that it's continuous from the left or continuous from the right. For instance, looking again at this greatest integer function over here, we could say that this function is continuous from the right at every integer. Do we agree with that? We could say this is continuous from the right. At every integer. Because the limit value is equal to the function value whenever we look at this from the right. Does that make sense? It's kind of fun when you get it. I think calculus is fun. I have fun teaching this. Let's see. It is somewhat unfortunate that, we're online, we're not in person. I would have liked to have, I like teaching calculus in person, but, this is fine too. It is safer this way, so. Until everyone can, get a vaccine if you want one. I'm getting my second vaccine in 2 weeks. I'm excited. Here we have, if you all turn on your cams, it's essentially the same. Yeah. Here we have another definition. We're going to define something being continuous on an interval. A function f is continuous on an interval if it is continuous at every number in the interval. If f is defined only on one side of an endpoint of the interval, we understand continuous to mean at the continuous at the endpoint to mean continuous from the left or continuous from the right. So this is another somewhat seemingly common sense definition, right? Something is continuous on an interval if it's continuous at every number in the interval, right? Does that make sense? Please hold. So if a function is continuous at every single point in a given interval, then we just say it's continuous on that interval. And this just says, again, if f is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left. Let's throw up an example here. I'll say one nice thing here is, one nice thing about online is a lot of these things take a while to write on a board, right? So we get to save a little bit of time in terms of me not having to write everything out. Show that the function f of x equals 1 minus the square root of 1 minus x squared is continuous on the interval -1 to +1. How can I even begin to do this? Use limit laws? Yeah. So the first thing that we're going to do is we're going to show that it's continuous on the interval, on the open interval. Okay. Just to clarify, this is what we call a closed interval. Whenever both of our endpoints are included with these square brackets, we call this a closed interval. You've probably seen the phrase open interval. You've seen this phrase a lot, right? In definitions. Right? Open interval means that it's an interval that doesn't include the endpoints. Does that make sense? So whenever I say that we're going to look at this on the open interval first, I mean that we're going to look at this on the interval -1 to 1, not including these endpoints. We're going to look at the continuity in terms of this, which is the same thing as saying that A is between -1 and 1 at first. Is this okay? We're first going to look on the open interval, and then we are going to show that the endpoints, we're going to show that this is continuous at its endpoints as well. Okay? So, the limit of f of x as x approaches a is equal to the limit of 1 minus the square root of 1 minus x squared as x approaches a. Using our limit laws, this is the limit of 1 as x approaches a minus the limit of 1 minus x squared as x approaches a. Is this okay? This is our difference law. The limit of a constant is the constant, right? And if I take the limit of a square root, I have a root law. That's the square root of the limit. Are we following so far? Is this okay? Yes, this is good. And now, which laws were applied? Let's see. Going up here, we have difference law. Let's see. Difference law. We have, oh wait, only the difference law here, right? We have the difference law. Between these two steps, we have, let me write this in a separate color. The constant law, is it called the constant law? I can't remember. I think we may have just called this the constant law. And we have a root law. The limit of a constant is just the constant. Because this is just a number, right? This number cannot change as x changes. Because this number can't vary as x varies, this number is always the number. Does that make sense? Cool. And now I can use direct substitution. Because this thing inside of here is a polynomial. So this is 1 minus the square root of 1 minus a squared. And this is actually equal to f of a, because f of x is 1 minus the square root of 1 minus x squared. So we say, because f of a is equal to the limit as x approaches a of f of x on the interval -1 to 1, this means that f of x is continuous on the interval -1 to 1. Does this make sense? We're not quite done yet, but we've proved that everything on this open interval, everything between these two numbers, that the function is continuous on that. What do we think about this proof so far? Does it make sense? Are we totally lost? I know how we got here, but I'm not sure what I'm doing. Okay, so what we're doing is, so the answer to what is this answer is we're not quite done yet. So we're trying to show that this function is continuous on this closed interval, -1 to 1. What we're doing is we're breaking this down into a few steps. We're breaking this down into show that it's, that f is continuous on the open interval, this open interval. Then we're going to show that f is continuous at endpoints. So we're going to show that f is continuous at -1 and at +1. And that will prove that f is continuous on the closed interval. Does that make sense? We're going to prove that it's continuous from the left and continuous from the right. And that will mean that it is continuous on that interval. So we have proved that it's continuous on that open interval. We haven't said anything about the endpoints yet. So I need to find, for instance, the limit as x approaches -1 from the right of this function. This is the limit as x approaches -1 from the right of 1 minus the square root of 1 minus x squared. This is a rational function. I'm allowed to use direct substitution here. Right? So if I plug this in, I get 0, right? And this is just f of -1. This tells me that this is continuous from the right at x equals -1. So far, I know that this is what tells us that this is continuous from the right at x equals -1. The fact that the limit as x approaches -1 from the right is equal to f of -1 tells us that this function is continuous from the right at x equals -1. The fact that the function value is equal to the limit as x approaches 1 from the, or -1 from the right, tells us that this is continuous from the right. Function value equals limit means continuity. Does that make sense? Function value equals limit means continuous. It's not because it well, yes, but it's because it equaled the function value. It's because it equals what you just get if you plug. Okay, if we find f of -1, this is 1 minus the square root of 1 minus -1, right? Squared, sorry. This is 1 minus the square root of 1 minus 1. This is 1 minus the square root of, oh wait, did I make a mistake? This is 1, sorry. This is 1, not 0, sorry. I was in a rush. Anyway, and this is 1. So f of -1 is equal to the limit as x approaches -1 from the right. Yeah, so that part is the part that, okay, because of this. This is the part that makes it continuous from the right. Irrespective of what number these two things are actually equal to. Does that make sense? So we've proved that this function is continuous from the right at x equals -1. And now we just need to prove that this is continuous from the left at x equals +1. And then we've proved that it's continuous on the entire closed interval. So the limit of f of x as x approaches 1 is the limit of 1 minus the square root of 1 minus x squared as x approaches 1, which is equal to 1. If we do the math here, it's going to also work out to be 1, because I can use direct substitution here. And this is what I get if I just plug 1 into the function. Oh, sorry. I should have had from the left here. Sorry. From the left. I can't say from the right also for this number, because I'm looking at a closed interval that ends with this number, right? I'm not looking at anything greater than 1 for this function. So, because, oh, I'm trying to erase. Okay, I was trying to select my eraser. This limit is equal to this function value. We say f of x is continuous from the left at x equals 1. Does that make sense? Yay? Nay? And we've proven that this is continuous at these endpoints of this interval. We've proven that this is continuous at the endpoints of this interval, and that it's continuous on the open interval that does not include the endpoints, right? So we've proven f of x is continuous on the interval -1 to 1, continuous from the right at x equals -1, and continuous from the left at x equals +1. So this means that f is continuous on the closed interval -1 to 1. This is our conclusion. Does that make sense? Oui. I'm not seeing very many yeses, so I'm taking that as a no. You think so? Oh, okay. Nice. Never mind then. You're good? You're losing your grip on reality? Oh, that's fine. Taking notes? Cool. Okay, so we have a small theorem that accompanies this. It's just properties of continuous functions. If functions f and g are continuous at a and c is a constant, then the following functions are also continuous at a. F plus g, f minus g, c times f, f times g, f divided by g, as long as g of a is not 0. Each of these follows from its corresponding limit law. Does this make sense? Sum of continuous functions is continuous. Difference of continuous functions is continuous. Constant multiple of continuous function is continuous. A product of continuous functions is continuous. And a quotient of continuous functions is continuous as long as the denominator is not 0. Yeah, no problem. Much continuity. Okay. We have a sister theorem to the direct substitution property. Any polynomial is continuous anywhere. So polynomials are continuous for all real numbers. And any rational function is continuous anywhere it's defined. That is, it's continuous on its entire domain. I leave the proof as an exercise to the reader. But do these make sense? These were, if not directly stated, perhaps implied from our direct substitution property. Show you the money? Nah. There's a proof of this in the textbook. Yeah. Again, I leave it as an exercise for the reader. Sorry, you can hear my dog crying in the background. For what he wants my attention. Let's get through a few more theorems real quick. This one almost, really, this This is almost not even worth writing, but here's another theorem. The limit of as theta approaches 0 of cosine of theta is 1, and the limit of sine of theta as theta approaches 0 is 0. These are kind of just logical conclusions from looking at our trigonometric functions, right? As a result of this, this is just saying that cosine and sine are continuous at 0. And we can generalize this to just say that these functions are continuous everywhere. So the real takeaway that we would attempt to get from this is cosine and sine are continuous everywhere. This also makes a lot of sense if we've these basic cosine and sine functions are continuous everywhere. If you start adding in like weird stuff in front of them, right? As long as I have these two things on their own, this is always true. Yes. Because you can look at the graph and you can draw these sinusoidal functions without ever picking up your pen, right? Now, the tangent function has some discontinuities though, right? Because tangent is sine divided by cosine. So tangent is discontinuous. Anywhere that cosine is equal to 0. This is at any odd multiple of pi over 2. Any odd integer multiple of pi over 2. Even multiples of pi over 2, the cosine function is 1 or negative 1. Oh no, I know that what you meant by pi over 2 is I know that in your brain you mean the odd multiples of pi over 2, right? I know that you didn't mean like pi and 2 pi and stuff. So tangent actually has an infinite number of discontinuities, interestingly enough. An infinite number. I'm sorry, sir. Jeez. Do you guys hear my dog yelling at me? Here's a few more functions that are continuous everywhere in their domains. Sir, you're going to have to apologize to the class. The following types of functions are continuous at every number in their domains. Polynomials, rational functions, root functions, trigonometric functions, inverse trigonometric functions. So this is true, right? Even though we just discussed that tangent has infinite discontinuities, those discontinuities are not in the domain of tangent, right? So tangent is continuous at every number in its domain. Exponential functions and logarithmic functions. Let me see. How much more stuff do we have to get through here? Ooh. Okay. Let's look at a few more theorems here. If f is continuous at b, and the limit as x approaches a of g of x is equal to b, then the limit of f of g of x as x approaches a is equal to f of b. So this is just saying that if you have a composition of functions, that the limit of this composition is equal to the value of plugging that inner limit in to the outside function. Does that make sense? You can find the limit of the inside and just plug that value into the outer function. Does that make sense? Yes. Okay. Okay. All right. There's kind of a bit of a corollary to this. Oh, and it's necessarily, this is probably more accurately considered a corollary. If G is continuous at A and F is continuous at G of A, then the composite function f of G given by f of G of X is continuous at A. Does that make sense? Writing so fast. Let's use theorem 8 real quick. Let's look at a problem involving theorem 8. Jeez, I'm sorry, sir. Just so you know, he went out recently. I was playing with him in the backyard right before this class. Let's evaluate the limit of arcsine of 1 minus the square root of x divided by 1 minus x as x approaches 1. Well, really, this is a composition of functions, right? I'm really taking the arcsine of another function. So realistically, I'm allowed to pull this limit inside the function. This is arcsine of the limit as x approaches 1 of 1 minus the square root of x divided by 1 minus x. Does that make sense? Yes? Okay. Then I can factor the inside, right? I can factor my denominator. I think it's going to be more helpful if we see that I can technically factor my denominator here to cause something to cancel. Because I could apply if I tried to apply the root law and use, well, at this point, since I have that whole list of functions, I could just go ahead and try to apply direct substitution here. But notice that direct substitution yields 0 divided by 0, right? So I don't want to try direct substitution just yet. But I could think of this denominator as a difference of squares. Do you agree that the denominator could be factored in this way? And then, this is the kind of creative thinking you're going to need in calculus, by the way. And then you have the limit as x approaches 1 of, notice that 1 minus the square root of x cancels, right? It's 1 over 1 plus square root of x. You can now evaluate that limit using direct substitution. right? This ends up being the arcsine of 1/2, because plugging 1 in, and what's the arcsine of 1/2? Arcsine of 1/2 is pi over 6, right? Because pi over 6 is the angle on the unit circle that has a sine value of 1/2 that is between negative pi over 2 and pi over 2, right? Which is the range of this arcsine function. Okay. And I'll just go ahead. I'll go ahead and I'll throw it up. But we'll talk about it in depth at the beginning of next class. We only have a little bit more. Of this section. This is the intermediate value theorem, where we get 1/2. Direct substitution at this point. You can just plug the 1 in. Yeah. So, intermediate value theorem. If a function is continuous, yes. Question.
I'm sorry to interrupt you. What is the name of the action that we performed when we changed the denominator of 1 minus x into, like, we expanded on it?
So we just factored. We factored because this is like a difference of squares, basically. If we wanted to do if it helps to think of it as it might help us if we say let u equal the square root of x. Then this function becomes 1 minus u over 1 minus, well, x would be square root of x squared, right? 1 minus u squared. And do you agree that we can factor 1 minus u squared as 1 minus u times 1 plus u? Does that help? Does that make sense? Cool. Yeah, no problem. So I'm just going to read this, and we will discuss it at the beginning of our next class briefly. So we're basically right on target. Suppose that f is continuous on the closed interval ab, and let n be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c in the open interval ab such that f of c is equal to n. This is just saying that if your function is continuous, right? If your function is continuous, you have to obtain every y value that occurs between any arbitrary y value, right? It's just saying that if down here is the point a f of a, and up here is the point b f of b, that you have to obtain every y value between f of b and f of a. Do we agree with that? If the function's continuous? Yeah, this is just saying if the function's continuous, then this function contains every y value between any two arbitrary y values. That's it. And we're going to look at this more in depth next class. Okay. Give me just a second and I will pay the dog tax. Hold on. It's like the range of f of a and f of b. Well, f of a and f of b aren't functions in and of themselves. They are values, they're y values in the function f. Let me turn on a light here, and I'll show you Dr. Doom since he's right here, and since class is over. Since I think some of you haven't yet seen Dr. Doom, have you? You haven't? Okay. Give me a second. Let me grab him. Okay. Oh, hello. Hello. All right, let me stop sharing my screen here. This is Dr. Doom. Say hello. You don't want to? He's not very large. What kind of dog is he? He's a mutt. He's like a Cocker Spaniel mix. Is he mean? Oh yeah, he's so mean. No, he's very kind. He only bosses my wife and I around. Everyone else is very nice too. He should teach the class. I don't know if Dr. Doom understands calculus, but I'll have a conversation with him about it. Yeah, he's turning 5 this month. All right, buddy, let's get down. Come on. Yeah. I think he's like demanding his food. So I'm going to go feed him and feed myself as well. So as usual, have a great rest of your night. And okay. And please email me with any questions. Remember, we don't have class for the rest of the week. Spring break now. So, but I'll answer any of your questions. And I will upload the lab either later tonight or early tomorrow. It'll just be a lab on 2.3, 2.5. Okay. And this week, we're only going to have 2.3, 2.5 homework. Reach out to me with any questions, please. I would like to answer them. That's what I'm here for. That's what I get paid to do. So allow me to work by assisting you. Take it easy, everyone.